say this seminar started in the morning, so I know it's tough to still be there. So thank you so much. So this is title of my talk. So I'll be basically going over all of some of the work that I have done when I was at LSU with Rob Lipton, and some of the new work that I'm doing as a side project, not as a main project because I'm funded for something else. So basically, right now I'm at Odin Institute for Computational Engineering and Science. I'm a postdoc here, and before that I was at LSU. And most of the work that you'll see is performed while I was there. So a first part of my talk is peridynamics, general theory, and its application. And this is done with Rob Lipton, who is professor at LSU, who just gave a talk. And then also with Patrick, we are doing a couple of projects which are open. We are looking at computational aspects of peridynamic, trying to develop a more massively parallel solvers for peridynamic. And towards that, we recently had this project in Google Summer of Code, where Patrick and I were mentors. It was sponsored by Google, and probably next year we'll have something along the line, so that we are basically in that direction with Patrick, where we can have a very useful, massively parallel solver for peridynamic, or in general for any non-local methods. Second part of my talk is on application of peridynamics to granular media, and there again Rob Lipton is there, and then I've been also working with Prathmesh Desai, who is a research scientist at Rice University. He's an expert in discrete element methods. So I was getting some useful feedbacks with from him, so that we can develop a nice hybrid peridynamics plus DM model. And then also recently I also started to talk to Devdeep, who also presented some of his work, impressive work, a couple of hours before. Okay, so this is my outline. So I'll basically give you overview of peridynamics. Then I'll mention two challenges and opportunities lying there, and then directly go to the application to mode one and mixed mode fractures. I'll show simulation results, but the idea behind those simulations are not just to impress you or show you, look, we can do fracture, but to bring out certain features of peridynamic through those simulation results. And I'll try to do that in the third point. And then I'll jump to PeriDM. We like to call it PeriDM. It's a peridynamics plus DM hybrid model for granular media, and give you the overview of the model, and then show you some list of results, preliminary results, which are promising. We saw that this hybrid model, has potential in the future, especially in applications where damage of individual particles can play a big role. Well, DM cannot certainly handle that. So through these results, I'll try to convey that in certain applications like those where a damage of a particle can play a big role, this model is a promising model. And then I'll talk about least couple of points on basically where we want to focus in let's say 6 months or 1 year from now. So first part, so a usual notation. So we denote x. X denotes a material point, typical material point in the domain omega, and then z is a current configuration spatial point. It's a sum of material point plus displacement u. We denote non-local length scale horizon by epsilon, and a relative stretch of bond between y and x is denoted by s. It's a basically change in length in current configuration divided by reference length. If you assume that u is small compared to size of the domain, you can linearize that relation, and you get what is there in the last part of the last equation, basically in terms of displacement difference. So internal force is, as we all know, so it's basically sum of pairwise forces, F at epsilon, and you are given some kind of constitutive law which relates this pairwise force with bond strain. And it could also be a function of two spatial points, there are two material points that we are at right now. So it is a function of strain, and also could be a function of y and x. A very simple example is a linear spring model. So you can imagine a linear spring with constant k between y and x, and you can write down the pairwise force because of that spring with k stiffness, which is here. And this is basically a linear elastic peridynamic model. It's basically slope defines linear strength of a material, and it does not break. It cannot break. It's just linear all the way through all range of strengths. With when U is smooth, again we all know that. So it basically is a good approximation of divergence of classical stress or Cauchy stress, where you have elasticity tensor, which is basically dictated by your constant in the peridynamic model C. And you add the fracture. Basically you say that, okay, if my bonds are stretched beyond SC, I'll break the bond. I'll have zero force, and that's the way you get add a fracture to the model. And fracture basically is a collection of broken bonds. And a very important remark that we all know already. Again, this I think most of it we all know, so I'll anyways repeat it. So C, the slope of this profile dictates elastic strength of a solid, whereas SC, critical strength, determines the fracture strength of a media. And instead of considering this kind of a fracture model on the left, what we do is regularize it with this smooth potential function, and we have this softening model. And some of the results that I saw in my first part of my talk is mostly obtained using this softening model. One of the benefits of this softening model, as you see also from Rob's talk, is that you can do a lot of theoretical study with this kind of model. Like, it has really nice features. You can show well-posedness in Hoelder space, in Sobolev space, and that enables you to very rigorously do a priori error estimates on piecewise constant approximation or finite element approximation. So that's really nice. Okay, so this is a full set of equations. So you have balance of linear momentum on first, and then you have a balance of angular momentum ensured by this pairwise form of pairwise force. So this is a typo. Instead of by, it's a bold y. So it's a latex typo. But balance of linear momentum is really ensured by having this kind of relation there. And you are given a boundary condition, or you prescribe a displacement on non-zero area in 2D or non-zero volume of the domain in 3D. And then you're also supplied some kind of external force, either near the boundary or in the body itself, in the bulk. And you are also given initial condition in displacement and velocity. So like I said, I'll just flash this slide. This is not the main topic, but I just wanted to convey the point that with this kind of softening model that I talked about, enables you to prove existence of solution rigorously in nice spaces, which again enables you to do more things later on. And we have attempted to do we proved existence in Hoelder space and then Sobolev space, and then use that to find a priori error estimates on piecewise constant approximation or finite element approximation. So this is nice. Okay, so I'll two slides, this and next, I'll basically talk about challenges and opportunities. So you have refined the mesh, and if your contrast of horizon to mesh size is large, so it's challenging. So it's computationally very costly. So one of the approach which is very active these days is local non-local coupled methods. Not these days, like 10 years, I'll say. And it's still active in the sense that many of these methods are ad hoc in some sense. So people are still trying to develop a coupled method where some of the ad hocness you can remove, and it's some of the problems that arise because of non-local and local coupling, like material properties are completely different. How the material behaves in local model compared to how the material behaves in non-local model are different, and because of that you can introduce a spurious effects in a displacement. And to alleviate that, people are trying hard, but it's still an open problem, I'll say. So this is one of the areas where we have opportunity lying there. So it's difficult because like people have already mentioned that peridynamic has wave dispersion, which is not present in local model. So when you have a domain where in one part of the domain you have local model, in another part of the domain you have non-local model, you can see that there's a problem because of dispersion already. So you can, yeah, basically a material could be incompatible at the interface, and this could introduce either spurious effects, or it could also cause a discontinuity in fields. So second opportunity is basically in extension of aerodynamic, like the model to alloys, super alloys, and along that line, you can basically, by tweaking this pairwise force, by enriching this pairwise force relation with certain more physics, like you can have a damping there, or you can have a memory effect, or you can also have the bond strength in that pairwise force have depend on a corrosive field. So by doing that, by just introducing many physics or different physics at the bond level, you can get, the physics holding at the continuum level. So in that sense, it's nice thing that by just looking at a simple spring model between 2 points and just thinking that, oh, what can I do more there, and when you do that, and then the result, you see some really nice results at the continuum level. So we in 2018 we did this experiment where we had this we proposed new model, basically where we had memory in the pairwise force, and the memory was such that every time you stretch a bond beyond certain threshold, it will lose the stiffness. So when you stretch a bond beyond certain threshold and you unload it, it will come back with a smaller slope, and you keep on doing that in cyclic loading, like that happens, you'll see that every in every cycle it will lose stiffness in certain proportion. So that we did in 2018. But another promising area or application of peridynamic is in bringing out effect of corrosion, or including effect of corrosion on the basically on the continuum media. And this is pursued by Florin Bobaru. He has like quite a lot paper in this area, so you can check it out. Okay, so this is third part of my first part of my talk. So basically application of peridynamic to fracture in solids. So first point is localization of damage. So I'll first go by defining what is process zone. So process zone is basically a simple definition. I'm not being strictly rigorous here. So it's a region of points where one or more broken bonds, you have one or more broken bonds. And in this region, strains are typically high compared to region where displacement are small. The width of process zone, at least for the bond-based model that we have experimented on, is about 2 epsilon with plus minus some mesh size. And then this width goes to 0 as epsilon goes to 0. So process zone shrinks to a curve or surface. And then as epsilon goes to 0, strain basically blows up. So you have more, higher and higher strain, and ultimately, I imagine if epsilon is really 0, it will be infinity, indicating that there you have a discontinuity in the displacement. So in some ways, for fixed non-zero epsilon, what you see is peridynamic is a regularization of a fracture in which discontinuity in the displacement in LEFM model along curve or surface is replaced with process zone, where you have a bounded strain. Although the value of strain is much higher, but it's bounded and it's limited to a very small region. Okay, so now show that numerically, that that is what is happening in numerically also. So this is a very simple setup. So we have a mode 1 crack, or the horizontal crack shown in red at the middle point of a vertical edge in the figure. And then on top and bottom, we are applying a body force on very small area. The depth of this region where we're applying body force is equal to epsilon, the horizon. And the body force has this form. It's basically some fixed number divided by epsilon. So every time you refine the epsilon, every time you change the epsilon, body force will scale accordingly. And since you change the epsilon, the region at which you are applying body force is also shrinked. So what it basically does is, if you compute the net force applied on top and bottom, you'll see that it is independent of epsilon. So net force is basically, and why we want to do that is basically because we want to compare results for 3 different epsilons, and it's only fair to compare results for 3 different epsilon if the external conditions are kind of same in some sense. It's not same point wise, but in every sense it is same with this kind of body force. Okay. So this is a result where we basically look at two times process zone in red. And you see that in A you have a bigger epsilon, in B you have intermediate epsilon, and in C you have smallest epsilon horizon. And you see that thickness of process zone is shrinking. And here we plot the figure on top of each other, and then we basically look at process zone for three different epsilon, and it's very amazing this result that uh, process zone for a smallest epsilon shown in light yellow is basically encapsulated by a process zone for in intermediate epsilon shown by uh, dark yellow, and that is again encapsulated by process zone for biggest epsilon we have in the model, in the simulation. And this is really nice. So you can really see that process zone of smaller epsilon is a subset of a process zone corresponding to bigger epsilon. Okay, so that shows the localization of crack. Now I want to focus on this crack propagation and how this peridynamic model can capture the boundary effect. Again, this I think this previous result and this result is already demonstrated to you by Rob, but I'll just flash you those results again. So we have a mode one crack again, and then it's a length of the domain is high because we want a crack a little bit away from its initial length to fill the surface effects. So that's why it's a long length domain. And on top and bottom, we are applying a displacement boundary condition in vertical direction. So this is a displacement opening, a crack tip opening. So you have a plot of crack velocity divided by Rayleigh speed, and then you see that it is stabilizing at 0.6 value, which is also observed with this kind of same material parameter experimentally by one of the experiments by J. Feinberg. So I think that is also nice that we can observe what is also observed numerically, what is observed experimentally by different people. Okay, so I wanted to make this talk very quick, basically. So I just have those many slides for first part of my talk, and then I quickly want to move on to second part of my talk, which is peri-DM. It's basically peridynamics plus a DM hybrid method. So motivation and objective. So DM-based method introduce restrictions like it can only do spherical or circular shaped particles. It assumes that particles have rigid body motion. And there are applications where this particle attrition under extreme loading conditions or particle damage, a change in shape due to deformation and particle breakage can play a big role. So we are catering to those kind of application where you require a high fidelity model where where the damage of particle can play a big role. So goal is really to develop this high fidelity model and use peridynamic for the intra-particle deformation, whereas use modified DM like law for interparticle deformation, interparticle interaction. So this work is really motivated by 2018 work by group at UT Austin, basically by Foster and all et al. And they had this they introduced this idea that you use peridynamic for intraparticle interaction, whereas you use some kind of normal contact law, just normal contact law for between two particles, which is also in a way non-local, but the length where the particle at the near the boundary can see the particle in the opposite nodes at the particle of opposite particle is about mesh size. So it's a non-local idea, but the typically the critical radius, you'll see that we keep it as 0.95 of mesh size. So yeah, I'll not go more into that. So I think it's a non-local idea, and it has a similar non-local like what you have for internal forces in a media, like you do non-local calculation, a similar non-local contact law also for particle or two different particle can be introduced. But really this idea was introduced by these people, and then we got motivated by those models, and what we thought is we can do more, we can be more specific in this interparticle context. We can learn from DEM based methods and bring in many of the features that we see in DM based methods. Okay, so key idea is this. So you apply contact forces between discretized nodes of particle, as Devdeep also presented to you. So you may look at these two particles in figure A, and you zoom in the region where you think they may have a contact. So two nodes of two opposite particles Z and Z prime. You imagine that these are connected by some generalized spring dashpot system, where you also saw we are also showing resistor, which basically signifies the friction force that we have in the model. So it is connected by linear spring, so with modulus Kn, and then it has damping viscosity beta n, and then it has resistance, or which we see it as a friction coefficient. So you imagine that, and this system is only activated when Z and Z prime are very close to each other. So it is not there if the two nodes of two different particles are far from each other. So this is how it's done in DM based model, as you see in the reference there. So we just thought just apply the DM based model where in typically in DM Z and Z prime are a particle, really not the discretized node. And you can do the same with this discretized node. You can treat them as a particle as they do in DM, and then apply similar contact law here. So I'll go. So this is a very standard test that people do in DM. So they basically compute coefficient of restitution, which is square root of h1 by h0. So h0 is a distance between two particles, surface to surface distance, before they have collided. And then h1, and the particle on top is free falling. You are not prescribing any velocity. And h1 is the height, the maximum height the particle in red achieves after first contact. And using that h1 and h0, you compute coefficient of restitution. And if C of r is 1, that indicates you have a elastic collision. So there is no loss of energy, meaning a particle which has dropped down from h0 height, it will bounce back to the same height again. So it's 1. But when CR is less than 1, then you have some kind of dissipation of energy, which causes the particle to go to a smaller distance upwards. And CR apparently is a property of two particles in contact. So for example, glass and glass, if glass is colliding with glass, CR would be different compared to steel colliding with steel. So CR is really used to calibrate this damping parameter in the model in DM. And we can also, you'll see that what I saw in this result is basically try different damping parameters in the, so as epsilon bar n is gets smaller and smaller, you increase the damping effect further larger and larger. So basically when epsilon bar n is 1, you have no damping. So CR is 1. When epsilon is slightly below 1, you have certain amount of loss of energy. So you have some C of R. And as you keep on reducing epsilon, your energy that you are dissipating will also increase. So in that sense, this epsilon n could be used to calibrate this parameter by looking at two particles and just looking at the data and finding that what is the C of R for two particles of the two particles of different material properties, what is the CR for that, and then use that to find the epsilon n. So that gives you the way to calibrate the damping part of our model. And this Kn part, the spring part of the model, as Devdeep also presented to you, that expression is typically related to the bulk modulus, bulk strength of two particle in contact. So Kn is already determined by what is the strength of these two particle in contact. So you only need to use C of R to calibrate the beta n. And then you calibrate the friction coefficient using angle of repose test. So you let the, let's say, hundred or thousands of particles just settle down, and they will make certain angles. They will make certain angles, and this angle is used to calibrate the friction coefficient. Okay, so this is a two particle simulation in figure 1. I do not have damping, so it will bounce back to the exact same height from which it was dropped. And then figure 2, I have some amount of damping. And then in figure 3, it's basically two different radius, and I have some damping. It should bounce back to basically touch the upper outline upper edge basically. If it does not have dissipation, but if it has dissipation, it will not touch the upper line. Okay, so that's done. So next, what we could do is assign initial velocity to this particle, top particle that is colliding with the bottom particle. And with different increasing initial velocity, you can imagine that when the velocity is too high, you would expect that particle which is colliding to the bottom particle will break. A bottom particle will be unaffected because you freeze all of the displacement of that particle, so you will not see any damage. So you would only expect that top particle breaks because of this high velocity impact. So okay, and then we thought we should do some kind of study of mesh effects. It's still early, but basically what we did was we refined the particle further and further, and computed the C of R with this two particle test, the value of C of R, and we saw that since the contact radius is fixed by 0.95 of mesh size, so every time you have a refined mesh for the particle, you basically reduce the contact radius. uh, I think the possible explanation that when you have a fine mesh, you see less dissipation of energy because C of R is increasing as you refine the mesh, is because contact radius is small. Therefore, the duration of which these two particles are in contact in this dynamic simulation is smaller, and therefore it results in a less energy dissipation for finer mesh. But this is very early explanation. We plan to look at these mesh effects more rigorously in coming time. So let me check the time. So I'll finish in 2 minutes. So basically, this is two particle and wall test. So you have both top and bottom particle free. Wall is fixed, and top particle is assigned some high initial velocity. And this is a test where we had this 25 particles of radius given by uniform distribution, and then also displaced horizontally so that centers of this particle do not align vertically, and the wall on top is moving downwards. Ultimately it will crush these particles. So this is a simulation of that setup. Right. So here, what I really wanted to do with this simulation is that I wanted to compute reaction force felt by this top wall while it is moving downwards. And I would, if one would have lot many particles in there instead of just 25, what one would see is basically reaction force will go up because particles are intact, they are resisting very well this wall that is moving below. But ultimately damage will initiate, and damage will percolate to many other particles, resulting in yielding of media. So basically the idea of this simulation is to basically uh, find effective strength of this particulate media, and so at what penetration, at what impact, or what amount of displacement downwards it will start to yield. It's still not there. This plot is almost there, but it's still not that perfect. So, but I just have it anyway. So, okay. So future work. So we are working on development of novel methods that basically reduce the computational cost. You are doing non-local pairwise for each particle, and then you're also doing this non-local contact force in a way, because for individual nodes of particle, you are searching for other nodes in opposite particle if it is in contact radius or not. So that's a non-local search basically. So these are all makes this whole high fidelity model very costly. So we are working on some kind of novel methods that will reduce that. Then we are working on application of the model to engineering problems, and also thinking of including some kind of corrosive effect and lubrication effect to the model. And that is it. Thank you.